Hi, welcome to video 2.3G. It won't be as long as the last one, I promise. Okay, increasing and decreasing. Let's change that to speed. And recognizing limits at derivatives, which we've already seen, by the way. Okay, so just before we get into increasing and decreasing speed, let's talk about numbers 9 through 10 on this worksheet. I've recopied that, but here they are right here. Okay. So a particle is moving along a line according to the given equation where s feet is the directed distance from the origin at t seconds. There's 3 questions. In red, find the time when the instantaneous acceleration is 0. And then blue, find the directed distance of the particle from the origin. And then in purple, find the instantaneous velocity at that time. Okay? So they want to know at what time is the acceleration 0? Well, to find the acceleration, we got to start by using the position function, which, by the way, they will give you. Here it is again. We're going to be doing number 10. So they give you the position function. Notice this time they are saying t is greater than or equal to 0. Do not assume that that's true. If it doesn't say that, then t can be negative. Okay? All right, so here's the equation they gave us with t is greater than or equal to 0. Obviously, if we want to find out when the acceleration is 0, we need the acceleration, but we're going to need to get the velocity first because the acceleration is the derivative of the velocity. The velocity, of course, is the derivative of the position function. So there's the derivative of the position function, giving you the velocity, and then you take the derivative of the velocity to find the acceleration. So very easy to determine when the acceleration is 0. That's when 12t minus 12 is 0, which is at t equals 1 second. The second question, find the directed distance of the particle from the origin at this time. So at this 1 second, we want to know what is the position. So we take the position function, we place all the t's by 1 second, and we get -5, which means it's 5 to the left of the origin. Last question, what's the instantaneous velocity at this time? So we need the velocity at t equals the time we found in part A. Of course, the velocity function is up here, 6t squared minus 12t plus 3. We place the t's by 1, and that velocity will be -3 feet per second. So it's velocity, which is distance per time. This is distance, which is in feet. This is time, which is in seconds. Okay, but now we're going to get into increasing, decreasing. So let's kind of just look at the question for the time being, again from the worksheet. Particles moving along a horizontal line according to the given equation. S meters is the directed distance from the origin at t seconds. Find the instantaneous velocity, so that's our first question, and instantaneous acceleration in terms of t. So they just want the functions v equals and a equals with only t's. Determine the intervals of time when the particle is moving to the left, moving to the right. We know how to do that. Particles moving to the left when the velocity is negative, moving to the right when the velocity is positive. When is the velocity increasing? Well, a function increases when its derivative is positive, and the derivative of the velocity is the acceleration. So the velocity is increasing when the acceleration is positive. The velocity is decreasing when the acceleration is negative. However, these last 2 questions is what's new. When is the speed increasing? When is the speed decreasing? Okay, so we already know it's moving to the right when the velocity is positive. Hang on. Hello, sorry, that's my funky ring in my office at work. Okay, so we know that. We know the velocity is increasing when its derivative, which is the acceleration, is positive, and the velocity is decreasing when the acceleration is negative. The question is, how do you determine when the speed is increasing or decreasing? So I want you to picture this. I want you to picture that there's a car, and when the velocity is positive, that car is moving forward. When the velocity is negative, the car is moving backwards. And I want you to picture a tow truck that has a hook on the front. So the tow truck can either push on the car or pull on the car. And if the acceleration is positive, it's going to push on the car. If the acceleration is negative, it's going to pull on the car. So here's what we're going to do. We're going to look at the 4 different possibilities. Both are positive, both are negative. Velocity is positive, acceleration is negative, or vice versa. So if you were a car with a positive velocity, meaning you're moving forward, and a tow truck comes up behind you and pushes on you, wouldn't it make sense that your speed would increase? If you were moving forward and the tow truck pulled on you, wouldn't it mean that your speed would decrease? If you were moving backwards and somebody pushed on you, it would slow you down, so your speed would decrease. If you were moving backwards and somebody pulled on you, your speed would increase. So the way it works is pretty simple. If the velocity and the acceleration have the same sign, either both positive or both negative, then your speed is increasing. If they have opposite signs, your speed is decreasing. So here's number 12. This is the given position function. They are telling you t is greater than or equal to 0. So when you go to draw a number line, it's actually going to be a number array. So we're going to need the velocity and the acceleration. So we find the velocity, which is the derivative. And we ask ourselves, when is that derivative 0? Because remember, the first question that they're asking is, in the question, is determine the intervals of time when the particle is moving left and moving right. And we know the particle is moving right when the velocity is positive, left when the velocity is negative. So the first thing we're going to do is find out what makes the velocity equal to 0. So multiply both sides by 2, factor, and I end up with the velocity is 0 at t equals 6 or 2. So I put those on my number array. Remember, it's not a number line because the t has to be greater than or equal to 0. On the top, and you have to label what's happening. You can't just put pluses and minus signs here without telling me what they are. So when the velocity is 0, you know that happens at t equals 2 seconds and 6 seconds. Now, both of these exponents of these factors are odd. The signs will alternate. If I pick a number between 2 and 6 like 0 and plug it back into this factored form, 0 minus 6 is negative, 0 minus 2 is negative, a negative times a negative. Oh, I'm sorry, 0 is I can't pick 0, never mind. I have to pick 1 because 0 is one of the endpoints. So if I pick 1, which is in this interval here, 1 minus 6 is negative, 1 minus 2 is negative, negative times negative is positive. Signs alternate. When the velocity is positive, the object's moving right. When the velocity is negative, the object's moving left. When the velocity is positive, the object's moving right. So the object is moving right between 0 and 2 seconds, and from 6 seconds onwards, the velocity is moving to the left between 2 and 6 seconds. Okay, then they want to know when the velocity is increasing or decreasing, and that'll depend on whether the acceleration is positive or negative. So the first thing we're going to do is find the acceleration, which is the derivative of the velocity, and ask ourselves, when is it 0? Well, it's 0 at t equals 4. Now what's going to happen here is we're going to put that on a number line, a number array I should say, because t is greater than or equal to 0. And I have one number. So the signs will alternate because this does have an odd exponent. So what happens is, if I plug in a number between 0 and 4 like 1, my acceleration will be negative. If I plug in something like 5, it'll be positive. So if the acceleration is negative, the velocity is decreasing. If the acceleration is positive, the velocity is increasing. So the velocity is increasing for t element 4 to infinity and decreasing for t element 0 to 4. The last question asks you about the speed, and we need both the velocity and the acceleration to do that. Okay? So here's what we're going to do. You can make two separate number lines if you like. One for the velocity, one for the... So I'm just copying basically this number line right here, which is for velocity. Starts at 0, there's points at 2 and 6, and it goes plus, minus, plus, right? So 0, 2, 6, plus, minus the whole time between 2 and 6, and then plus. The acceleration only has a special spot at 4. So when I put this, I'm going to line up the zeros. I'm going to make sure the 4 is between the 2 and the 6. The whole time between 0 and 4, the acceleration is negative. So this whole time it's negative. The whole time to the right of 4, it's positive. But there's kind of these natural breaks in here, 0 to 2, 2 to 4, 4 to 6, 6 to infinity. You'll notice these two, I'm just kind of condensing that, minus, 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 plus, 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 and therefore you can now decide on the speed If they have opposite signs, the velocity and acceleration, speed is decreasing. Same sign, speed is increasing. Opposite sign, speed is decreasing. Same sign, increasing. So the speed is increasing from 2 to 4 and 6 to infinity, and the speed is decreasing from 0 to 2 and 4 to 6. And this is the last of the worksheet. We've already done this, recognizing the two limit definitions, the original and the alternative, and recognizing them as being derivatives. So when you look at number 14, we're hoping that you'll go, oh, look, it's the limit as h goes to 0. There's an h here. Doesn't this look like f of x plus h minus f of x? Now, it's actually f of x1 plus h minus f of x1. So your function is cosine of, and your x1 is pi over 6. So really what this is the derivative at pi over 6, where f of x is cosine x. If f of x is cos x, its derivative is negative sine x, and now I'm going to replace x by 5 pi over 6. That reference angle is 30 degrees. Your answer will be negative a half. Same thing here. The function is secant x, and the specific value we're finding that is at pi over 6. Derivative of secant x is secant tan. Replace the x's by pi over 6, and you'll get an answer. You can certainly pause on these if you'd like. This is recognizing the alternative form, which is even easier because you actually have your f of x sitting there, and this is your x1, and that's your x1. So obviously this is the derivative of f of x equals sine x, and you're finding that derivative at pi over 3. And that was very short. End of video 2.3G. And this is also the end of section 2.3. I was going to give a third video. I'm not going to because 2.3F was very long.